Hi, so this is the lesson on refraction that we did on November 19th. So we're going to get started. What happens when light enters another medium and why? So basically what we have to understand is light changes its speed when it enters another medium. This is the most important thing that light does. All other things that happen are effects of this phenomenon. So light changes its speed, and why? Because different medium have different optical densities, right? So we had the analogy like a room that was really crowded. You can't move as fast in because there's a lot of obstacles around, and it's the same thing with light and a particular substance. If the substance is very optically dense, which is a denser medium, so denser medium. If the substance is very optically dense, light can't move around as fast, so light moves slower in an optically dense medium. And an optically rarer medium is a medium that does not have too many particles in it, so the light wave essentially can move around really quickly, so light moves faster in what is called a rarer medium. Alright, so we have optically dense mediums where light moves slower, optically rare mediums where light moves faster. And we know that nothing can move faster than the speed of light in vacuum, which is 3 times 10 to the power of 8 meters per second, and this is speed of light in a vacuum, which is also denoted by the letter small c, right? And here we have to understand that this vacuum is the rarest medium because there's absolutely no particles in a vacuum, and there's nothing that can be rarer than vacuum. And this is basically where light travels the fastest, and all other mediums would be denser than vacuum. Okay, so we'll get back to what this means in terms of refractive indices, but what is the effect of all this? So we saw by experiment that when a light approaches a medium, let's say this is the rarer medium and this is the denser medium. So now I'm going from rarer to denser medium. That's what I'm going to do. So we know that light is going to slow down because it's going into a denser medium. And when it does this, it bends towards the normal. What does that mean? So if it had not bent, if there was no medium change, so to speak, the light would have just gone on straight like this. But what is observed is that the light bends towards the normal, and this is the normal, right? Forgive my arrow, that's kind of bad, but we will be defining a couple of terms here. We'll be defining that tomorrow, but all we have to know is that light bends towards the normal when it goes from rare to denser medium, because the wavefront that light travels, so this part of the wavefront is going to hit the medium first before this part of the wavefront. So if you have like a wavefront like this region is going to hit the medium first and slow down before this eventually hits the medium and slows down. So what that causes is bending. So this is just a what I think is a very clever mnemonic to remember. So if you remember R2D2, that's rarer to denser medium, bends towards the normal, right? And we can also have a there. So let's draw something like this. So this is the undotted lines where it wouldn't have deviated, but now we're going from a denser to a rarer medium. So denser to rarer medium, we know light speeds up, and in this case the light is going to bend away from the normal. right? And you can remember that denser to rarer away from the normal, right? So we just have to know these two things: what happens, why it happens. So this bending is an effect of the change in speed because different parts of the wavefront are changing speeds at different times. This causes an apparent bending in the light ray. I'll also point out here that if we have room, we don't have room. If you have a normal and the light ray is coming along the normal, there is no bending. There is still a change in speed. So light, for example, let's do denser to rare. Light does get faster here in the rarer medium, but there's no bending because in a wavefront, all parts of that wavefront are reaching this at the same time. So there's no bending that occurs when a light ray strikes along the normal, strikes the interface. We call this line that I'm drawing here an interface because it's between two media. So denser medium is like water and a rare medium is like air. So the interface is like the surface of water. So that's what the interface is. Okay. What is a refractive index? So a refractive index is basically a value that is given to a medium. So it's a property of a medium that shows us how much light slows down in that medium. So how much a light ray slows down is given by its index of refraction, and it's a constant for a given medium. And we assign the we assign vacuum to have a index of refraction of 1. So n is the letter that notes or denotes index of refraction. It's quite early. Okay. We see here that vacuum has the lowest index of refraction, and we note here that air has a very, 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 it's basically 1.0003 almost. That's essentially equal to vacuum, so we can approximate the speed of light in air is also the same as the speed of light in vacuum, although it's not exactly the same. Its air is slightly slower because it has a refractive index of slightly over 1. And this is important. As refractive index increases, the speed of light actually decreases. So a higher refractive index means light travels slower in that substance. So that's kind of important to wrap our head around. So this answer is no, we cannot have a refractive index smaller than 1 because a smaller refractive index would mean light travels faster, and light travels the fastest in a refractive index of 1, which is a vacuum. There's no substance in which light travels faster than what it travels in a vacuum, and therefore you cannot have a refractive index smaller than 1. So I know I said 3 here. We're only going to be doing 1 for now. We'll get to the others later on. The 1 formula is N equals C over V. N being the refractive index, C being speed of light in vacuum. C is always, whenever you see the small c, you just automatically write this constant. It never changes, 3 times 10 to the 8 meters per second. That's just a given. You should know that at all times. Don't look for the question, no, I don't have a C. It's just always this value, right? And V is the speed of light in that medium. So we do know that light changes speed in medium. So this is refractive index of the medium and speed of light in that medium. So these are correlated for a particular medium. If in water light has a particular speed, that means that water has a particular refractive index, and we get that by doing speed of light in vacuum divided by the speed of light in water. So I'll briefly go over a couple of these calculations. I won't actually calculate it. I don't have a calculator on me, but I will show you how to do it. So calculate speed of light in water. We do have to be familiar with rearranging this formula, N equals C over V. To rearrange this, I need to calculate speed of light in a medium, which is water, right? So I need to calculate V. In order to get V, I'm going to multiply both left and right sides of this equation by V, because right now V is in the denominator, and I can't solve for something that's in the denominator. So I'm going to cancel out these V's, and I get V times N equals C. This is a useless, well, more or less useless kind of a version for this equation, because I always know what C is, so there's no point in calculating it. But here what I can do is I can divide both sides by N, which means that V equals C over N. We also noted that in any given fraction, if I have A over B equals C over D, I can move things freely across the diagonal. So like cross multiplication, except I don't have to fully cross multiply. So I can write this as AD over B equals C, and I can then move the A down, so D over B equals C over A. So as long as I'm moving things along a diagonal, when I have two fractions that are equal to each other, they still remain equal to each other. So the denominator of this guy moves to the numerator of this guy. Denominator can move to the opposite numerator. And that's kind of what we've done here when we had our initial formula C over V. I've moved this up there and this down here. So I got this formula, V equals C over N. And now I can just sub in my values. 3 times 10 raised to 8 meters per second. N for water is 1.33. And I think we got 2.52 times 10 to the power of 8 meters per second as our answer. Not entirely sure about that, but in our calculator, we would be putting this in as 3e8 divided by 1.333, where the e stands for like an exponent, exp or ee, or times 10 to the power of x button. So putting that, typing that button is important because it saves us the use of brackets and unnecessary calculation errors. So very important that we learn how to use that button. Okay, next question. The speed of light in a medium is given to us. So we are given V equals 1.66 times 10 to the power of 8 meters per second. What is the index of refraction? So this is just our regular formula. C is a constant, always 3 times 10 to the power of 8. V happens to be 1.66 times 10 to the power of 8 meters per second, meters per second. We'll note that N does not have any units to it because you're taking the ratio of speeds, so the units cancel out. There's no ratios. So this is approximately 1.8, and this would be the refractive index, or index of refraction, of this particular medium. Right, so I will not do 3 and 4 because they're the exact same as 1 and 2, and I will just show you here kind of what to do. So here I see that light is bending towards the normal. And so if light bends towards the normal, that means we are going from a rarer to a denser medium. And that's how you label it. Here light is going away from the normal. So we are going from a denser to a rarer medium. Here light is going towards the normal. So we're going from a rarer to a denser medium. Here we cannot determine which one is denser or rarer, because we know that even if both ways we would still see the same effect of the light. It would just, because we don't know the speed, it would just not bend, so we cannot determine which one is rarer or which one is denser. But the other ones we can, where there is bending. Sorry this was a long video. I will see you in class.